Hi, in this video segment, we will cover some very important aspects of the factorial design of experiments and also do some case studies. Plus, we will try to integrate this part with the other parts we have already learned in this module. Basically, the ideas are very simple, so I hope to speed through this to the maximum extent possible. Now, the experimental designs, we've talked about a few already, right? The box Benken design, the Dollard design, and the central composite design, etc. In that line of things, one of the most fundamental experimental designs is what is called the 2 to the power of k design. This 2 stands for the fact that each factor will be tested at two levels, typically called the minus and plus levels or the low and high levels respectively. So each factor will be tested at two levels, and k denotes the number of factors that are there. So if you have two factors a and b, you will have 2 to the power of 2, which is equal to 4 experimental points in a 2 factorial design. If you had three factors, that means k is equal to 3, the 2 to the power of k design will contain 2 to the power of 3 experiments, that is 8 experiments. So we just have to remember the 2 stands for the number of levels in which each of the k factors will be tested. So that is the idea of the 2 to the power of k design, or what is called a 2 factorial design, right? Or simply factorial design with two factors. So if you look at the illustration here, I show both the geometry and the design matrix. This is a 2 to the power of 2 design because both factors, there are two factors here, which is called A factor and B factor. These are the two factors. You can even call them x1 and x2, doesn't matter. So these are the two factors. One factor is this and the other factor is this. And each of them will be tested at two levels. So low and high for factor A, low and high for factor B. Therefore, the experiments will be done at the corners of this square. All right. So this is one experimental point. This is the second experimental point, the third and fourth. And actually, when you do those experiments, they'll be run in a random order. So one of the experiments will be when both the factors are low. One of the experiments will be when both the factors are high. And yet another experiment will be when A factor is high and B factor is low. And the last experiment would be done at factor B being high and factor A being low. So these are the four corners of the square. So in the design matrix, one of the experiments, right, experiment number 1 is indicated as minus and minus. So that corresponds to this experiment that's done. Experiment 2, that is in the table here, is when A is high and B is low, right? So A is high and B is low corresponds to this. So this is run 2. And experiment 3 is when A is minus and B is plus. That means when A is low and B is high, so that corresponds to this experiment. And experiment 4 is this, when both A and B are high. So that is what this design matrix tells us. And please remember, this is called a standard form. You typically you will see in a standard form that the first column goes minus plus minus plus, and the second column goes minus minus plus plus. Okay, this is what is called a standard form, and you have to understand the experiments are not done in this order. The experiments are done randomly. For example, the first experiment may be run 3, the second experiment may be this particular run, and the third experiment may be this, and the fourth conducted experiment may be this. Okay, so they are run in a randomized order to conform to one of the pillars of experimental design, which is called randomization. And sometimes when both are low, right, you denote it by the symbol 1. Right? When you say 1, it means both the factors are low, or all the factors are low, as you will see later. And when they talk about AB, it means A is high and B is high. When they talk about small a, it means factor A is high and factor B is low. And when they talk about B, they talk about factor B being high and factor A being low. So if you look at this, I say all this because different textbooks do different notations. So this will be 1, this will be A, this will be B, and this will be AB. To say that both A and B are high, so that's the label AB. So that is what is shown in this particular diagram. If you come to the case where there are three factors rather than two factors, now K is equal to 3, and still each of the factors is tested at two levels, a low level and a high level. Here the factors are labeled as capital A, capital B, and capital C. So now instead of a square, we have a three-dimensional object, which is a cube. That is what is shown there. And 2 to the power of 3 is 8 experiments. And you can comfortably represent them as corners of a cube or vertices of a cube. You see there are 8 vertices, and therefore each vertex or each that corresponds to one of the planned experiments. So ABC will be when A, B, and C are all set at high levels. So that is corresponding to run 8 in a standard order. Run 1 is when all the factors are low, so it's denoted as brackets 1, and that would be this experiment. All right. So AC will be when A and C are both high. So factor A is high, so you are in this right side phase, and factor C is high, therefore you are in the top phase, so you are in this corner, and then B is low, therefore you are in the front vertex. All right, so that is where you are. So this is AC. This is BC for the same reason. You can work out the details. So this one is called the standard form again. This is the standard form. So the factor A goes as minus plus minus plus minus plus minus plus in this case, and factor B goes as two minuses followed by two pluses, two minuses followed by two pluses, and C goes as four minuses followed by four pluses. So what you see is there is a certain pattern that is associated with how we write the experiments in standard order. And for example, this experiment 6 corresponds to the experiment where A and C are set at high levels and B is set at the low level. So that would correspond to this experiment AC. So the 6 is also nothing but AC when A and C are high and B is low. Experiment run 3 that is denoted in the standard table is when A and C are low and B is high. So it corresponds to this experiment, right? This is experiment 3 in the table where A is low and B is high and C is low, right? So it's going to be in the left, bottom, and back vertex. So that is going to be this vertex and so on. All right. So you will see that it scales nicely from a two-factor design to a three-factor design. And if you have four factors, then you will have two cubes to represent, because if you have four factors, you will have 2 to the power of 4 is equal to 16 experimental runs in a factorial design, right? So 16 runs can be represented as vertices of two cubes. So you will have one cube like this for D is equal to minus 1. Factor D is going to be at low level. There will be a similar cube for D is equal to plus 1, where D is kept at high level, right? So you can represent it as two cubes, etc. So you will find these kinds of things in various textbooks or websites, etc., etc. All right. Now, there are other experimental designs that kind of advance the basic 2 to the power of k design, as you will see here. So this one is what is called a 2 to the power of 2 design with some center points. So you understand these four corners. In this case, A is the reaction time and B is the temperature. So this is the actual physical meaning of factors. So you have one experiment done at small reaction time or low reaction time and low temperature, one experiment done at high reaction time and high temperature, and the other two combinations, low reaction time and high temperature, and high reaction time and low temperature. So these are the typical 2 to the power of 2 design. And to augment those four experiments, this experimenter has done 5 experiments at the center point. That means at 0, 0, when both A and B are at their mid levels. So in terms of time, that would correspond to 35 minutes of reaction time and 155 degrees Celsius for the reaction temperature. So 5 experiments, these are the replicate points. And all of these 9 experiments would be run in a random order. So you would not do the first 5 experiments to be the center point experiments. That is not true replication. Or you do that experiment once and take 5 measurements. That is not replication. You have to come to that experimental setting of 35 minutes of reaction time, and 155 degrees of Celsius from various other experiments. You have to conduct that experiment in a random order. So you'll have runs 1, 2, 3, 4, 5, 6, 7, 8, 9. You'll have coupons where you might just say this is -1, -1. If you just go with standard form, you will have -1, +1, +1, -1, let's say +1, +1, and then 0, 0, 0, 0, corresponding to the 5 replicates at the center point. So these are the 9 experimental runs in, let's say, standard form. You would have 9 coupons on put inside a hat or something like that. You mix it well, and whenever you're ready to do an experiment, draw out a coupon randomly from that. And if, let's say, this coupon comes, you do the experiment where A and B are high at both high settings, right? So that is the kind of randomization which you must do. Of course, the principle of blocking should also be adopted, right? So this is a 2 to the power of 2 design with center points that serve as replicates. Okay, and then you can also have a 3 to the power of 2 design, which is what is shown on the right hand side. Basically, this 3 stands for the fact that each of the 2 factors, this 2 is again the number of factors. Here they are showing 2 factors, x1 and x2, so k is equal to 2, but each of the factors is going to be tested at 3 levels: low, mid, and high. So if you take this factor x1, this represents the low, which is -1, the mid is represented as 0, and the high is represented as +1. Similarly for x2, low, medium, and high. So what you're doing is these 9 experimental points shown in a square, the vertices, the center point, and then the mid part of each of the 4 edges, right? Together make up the 9 experiments. This is a 3 to the power of 2 design. Again, 2 factors, and each factor run at 3 levels: low, mid, and high. And then there are other designs like the central composite design, CCD. We already looked at it in video segment 1. So basically what you do is the 4 factorial point experiments. So these are the 4 corners which we are familiar with now. Then you do a center point, and then you do these 4 axial points, right? 4 axial points, or what are called as star points. All right. So this is the case where k is equal to 2. You have 9 experiments, let's say, without replicates. So 4 experiments at the corners of the square corresponding to low, 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 high, high, low, and high, high. Then you have a center point experiment which corresponds to mid, mid. And then you do 4 experiments outside of the square, right, at the axial points, which are located at a distance of alpha from the center, right? So that is what is indicated here. Typically, alpha can have a certain value. For example, alpha can have a value like √2, which is absolutely fine, right? So something outside, you can decide the value of alpha, but it will be outside the square typically. The same thing in a 3-factor space will be denoted by this. So you have the vertices of the cube. So you have 8 experiments there, and then you have a center point experiment. So that makes it 9. And then at a distance away from each face of the cube, each of the 6 faces of a cube, you have these axial points or what are called the star points. There are 6 of them. Therefore, you have 8 vertex points plus 1 center point plus 6 axial or star points. Typically, the axial points are outside of the cube. All right. So you have a total of 15 experiments here. So this is called a central composite design in 3 factors. You can do the same thing in terms of 4 factors or 5 factors, etc., except that the visualization can become a little bit difficult or cumbersome. So you deal with that using software or just tables, etc. But these all have been formalized quite well in the research and practice literature. Now, the point that is being made here is that you can locate the axial points within the cube, or you can have it outside the cube. So what I showed here is the axial points, the 6 star points are outside of the cube, but you can also have the 6 star points located on the face of each cube. Instead of projecting outside of the cube, you can have it on the face of the cube itself, right? So you can have it as internal, or on the face of the cube, or outside the face of the cube, right? So all those variations are possible. In any case, in the design without replicates, the central composite design for 3 factors will have 15 experiments, right? 8 corners of the cube plus 1 center point plus 6 related to each face of the cube. All right, so you have 15 experiments in the central composite design. Box Benken design we have already seen. The experimental points are located at the surface of a sphere. For example, if it is a three-dimensional search space involving 3 factors x1, x2, and x3, so you have a sphere of radius square root of 2. On this sphere, you have the experimental points located, with some experiments run in replicates located at the center of the sphere, right? Here it is shown in a cube, it's not shown in a sphere, but you can also imagine a sphere that corresponds to the experimental points occurring on its surface, right? So that sphere will have a radius of square root of 2. So this is what box Benken design is, and we have already seen it in the first video segment. So these are the replicates, and the interesting thing is all the 3 factors are tested at 3 levels, right? For each factor you will see -1, 1 and 0 appearing, no other numbers. So 3 levels for each factor, but for 3 experiments, right, typically what you will do is 3 levels, 3 factors, you will have total of 27 experiments if you do a full factorial design, right? You understand? 3 factors, x1, x2, and x3, each of them run at 3 levels, low, medium, and high. So 3 to the power of 3 will be 27 if you do a traditional factorial design. But this box Benken design kind of does 3 levels in 3 factors using only 15 experiments, and that also includes replicates. So that's the power of the box Benken design. All right, so that is something that you may want to note. So let us do a few case studies to just firm up our ideas and to also begin to apply whatever we have learned so far. Now, this case study one is, it depends on, it comes from dyeing industry, D-Y-E-I-N-G, which is used to color, for example, fabric and stuff like that, right? So basically, the engineers or the scientists there have tried to narrow down on the number of factors that is going to affect the shade of the dyed material. So this is the output variable of interest. The shade reading is the output variable of interest, and the engineers feel that material quality M, oxidation temperature T, and oven pressure P are the 3 factors. So x1, x2, and x3, you can also call them M, T, and P, or M, P, and T, whatever that is. Those are the 3 factors affecting the shade reading Y. So it is like this: M, P, and T affecting the shade reading S. So this is the idea. These are the causal factors, if you like, for output. So you can generically call them as x1, x2, and x3, and S as Y. All right, so this is what it is. And as you can see, 8 experiments have been done. There are no replicates, and this is the standard order because minus, plus, minus, plus, minus, plus, minus, plus for first factor, minus, minus, plus, plus, minus, minus, plus, plus for second factor, 4 minuses followed by 4 pluses for the third factor. So this is what is called a standard order. So the experiments are labeled as 1 to 8. So one experiment is done at low value of M, low value of P, and low value of T. At that combination, an experiment is done, and the shade reading was found as to be 189. Another experiment was done with material quality set at high value, pressure and temperature at low values, and the shade reading was 228, and so on and so on, right? You see the meaning of these 8 experiments, and note that they were not done in this standard order. The first experiment was actually this experiment that was done, what is called as experiment number 8, corresponding to all the 3 factors being high. That came out in a randomized setup. That came out to be the first experiment to be conducted. The second experiment to be conducted was the experiment that is labeled as 7, right? And so on. Third experiment was this one. So the run order is different from the standard order. So that is something. And here, right, what happens is they say a shade reading of 200 is desired. So usually, right, when I used to work for chemical companies in the past, what happens is we would make certain products, right, certain grades of products with which gives some, let's say, the shade readings like this. And suddenly, existing customer or a new customer will come and say, I want to make a product with shade reading of 250. Can you kind of provide that product? And so what we will do is we have a model for this process relating MP and T to shade reading. So we will invert that model. So previously I said, right, M, P, and T affect S, right? So that is what you see here. As you change M, P, and T, the shade reading changes, right? So these are the causal factors and this is the response. So you may have a model relating S to M, P, and T. So let's call it beta naught plus beta 1 M plus beta 2 P plus beta 3, just as an example, PT. So let's say this is a good model for the process. Okay, just assume that. So now what happens is we have this model. That means we know the values of beta naught, beta 1, beta 2, and beta 3 because we have used historical data to figure out these parameters. Now, when somebody comes and asks for a target value of S, let's say the new customer wants a product with shade reading of 250. So we'll substitute S is equal to 250 here and try to find out the values of M, P, and T using this model that is likely to give us the value of 250. Of course, we know there are multiple combinations of M, P, and T that will give us 250. Why? Because from one equation, you are trying to find out three unknowns, right? So the point is you have to fix two in some sense, and then the third one you can find out from this equation. All right. So you're going to have multiple solutions to say the least because you're trying to project from a one-dimensional space to a three-dimensional space, right? So that reverse mapping will give you different or infinite combinations of MP and T. And typically we will find out a combination that is economical to us, that is not very far from our historical values of MP and T. So we will extrapolate lightly, if at all we need to extrapolate from our current settings in order to kind of satisfy the needs of that particular customer. So that is how we will use the model in an inverted fashion. And we will also utilize optimization techniques and other information like economics information, safety information, and so on in order to find out MP and T that will give us a shade reading of 250. And please note before going ahead that all these numbers are prone to error, measurement error, etc. So 189 is not really 189. It could be 175 or 192. It could be something, right? Because all measurements are corrupted by noise. So with all that into account, what we are trying to say here is this is an experimental campaign that is done in order to find out the model relating M, P, and T to S. And once we have that model, we want to make use of that model to achieve a shade reading of 200. So that may be the goal, because a new customer comes and says, I want to have a shade reading of 200. All right, can you produce that product? So but if you look at this data set, right, you might say, well, oh, luckily, right, 200. So use high value for M, high value for T, and low value of P, and we would satisfy this customer. Yes, it is true, but this 200 may not be actually 200, right? It may be actually one experiment, right? So the actual value could have been 196 or 207. We do not know. This 200 is a value with noise, with possibly some noise there. So, and we turned out to be lucky that, this 200 matches exactly with what is desired, and therefore our answer is this or something very close to this. Okay, but the numbers can be quite different. Somebody might want something like 225, in which case, you can have some answer close to this or this settings, right? So we have to use a model in order to um, kind of come up with recommendations, etc. Please remember, uh, tables memorize the data. So if something is in the form of a table, right, it just memorizes the data. It's a record of what has been observed in the past with errors, etc., etc. But a model generalizes. That's the power of a model. That means you take into account the effects of noise. Your model ignores things that are not important, things like that, right? So you get a more generalized understanding of the process, and generalization is key. Memorization is not the key, right? So that is something we need to remember, because now Google memorizes everything, right? So yeah, you don't have to memorize stuff these days. What we have to learn is to kind of generalize, to transfer skills from one domain to the other, etc., which as of now, something like Google is not able to do, though it is trying to get intelligent with artificial intelligence kind of things, working on giving human-like intelligence for that. So the point I'm trying to make here is we should not rely on tables, though tables are the source of data from which we make our models. But models are better abstractions of the physical phenomena. All right. So these 8 experiments that you see in this slide can be put in this conveniently in this cube form. So you show the 8 corners. Material A is low, material type B is high. Oven pressure can be a low value and a high value. The oxidation temperature can be a low value and a high value. So if you look at material, right, that's a discrete variable because we have only 2 materials. One is a low grade material called material A. Other is a high grade material called material B. So it's not a continuous variable, right? That is what it seems like, material A and material B. We do not know if we can tailor materials that is between A and B. So material I would consider to be a discrete variable. It can either be A or B. All right. Whereas oxidation temperature can be set at any value between low value and a high value. Likewise for oven pressure. So in any case, the experiments are represented as corners of the cube. And if you look at this experiment 2, which is 238 shade reading. So this is the shade reading. This is the experiment number 2. And that is what is shown here. This is the experiment number 2. That is what is shown there, which has material as minus and the pressure and temperature as plus. So that is what you see here in 238. Material is low, which means material A. So you are in the left face of the cube. And then oven pressure is high, oxidation temperature is high. So because the oxidation temperature is high, you are in the top face of the cube. And because the oven pressure is high, you are in the back face of the cube. So you are left, top, and back, which is this particular point. All right, so that is what is shown here in a nice graphical form. So some people may like this, some people may like a representation like this. All right, and so what we are now interested in is to find out the effects of M, P, and T. What is the effect of material? What is the effect of pressure? What is the effect of temperature on shade readings? We are also interested in the effects of interactions, material times pressure, material times temperature, and pressure times temperature. So these are the 2-factor interactions. You want to see if they have an effect on the shade reading. And finally, we would like to know the effect of the 3-factor interaction, M, P, and T, right? M times P times T, does it have an effect on the shade reading? So that is where we are trying to proceed. And then you can do it in 2 ways. One is through a simple addition, subtraction, averaging kind of idea. The other way we can do it is you take this data and try to build models and see. Both are very congruent approaches. There is no difference. Although, you know, for higher order systems, you cannot visualize, and therefore you would be better off going the regression route. That is why we covered linear regression before we came to this. All right, but let me illustrate all of them through the case studies that we have here. So this is what it is, and now this is an expanded input space. So this and this you've already seen in the previous thing as M, P, and T. So what you see here is M times P, M times T, and P times T. So these are the 2-factor interactions. So these are the 2-factor interactions. This is the 3-factor interactions. All right, so that is what it is. So how do you get this column M times P? You take M and you take P, minus and minus, you multiply minus and minus because it is M times P, the interaction. Minus into minus is plus, so you get a plus there. So if you take this particular thing, M is plus, high, that means material B, oven pressure is low, so plus and minus, so M times P will be plus multiplied by minus will be minus. So that is how you fill this column. Likewise, you can do for m times t. For example, if you want to know why this is plus, because this is m times t, so you look at m, you look at t for the corresponding experiment, minus and minus. So if you multiply the two, you will get plus, and so on, right? You can do p times t and m times p times t. So whenever you see a minus, basically it means low value, and whenever you see a plus, it means high value. Of course, physically only you're changing m, p, and t. These are derivatives, right? That means you can derive them from m, p, and t readings, right? So these four columns are synthetically constructed. They don't have a physical representation in the real world, though they are useful in a mathematical or statistical sense. So you show the run order here, and you show the output value, the shade reading here. Okay, so this is the expanded input matrix that takes care of the actual physical inputs and the two-factor interactions and the three-factor interaction. So that is what this is about. And then you can compute the effects now quite easily. So how do you get this effect to be 22? I'll show it to you as diagrams in the later slides, but this 22 is obtained by taking all the readings on that column with a plus sign, right? So I'm going to take this, this, and this because they all have a plus sign. So I'm going to take the average of those four readings. I'll take the average of the plus readings. So this is the average of the shade readings when material column shows plus. And then in a different color, let me just show you the shade readings when material column has a minus entry or a low entry, right? So you have this, 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 and this. So you take the average of those four readings, right? You take the average of those four readings. So these represent the average of the negative readings for material alone. So if you take the averages and then you subtract this and this, right? So you take this number and then from that you subtract this value, you will get 22, as you will see in the later slides. So this is the effect of material. So if other things being the same, if you change the material from A to B, you are going to get an increase in shade reading of 22. That is what it means on the average. All right, on the average, the effect of material going from low to high value is going to be plus 22. Likewise, you can do it for other uh, columns right there. So if you want to find out this effect, right? For example, if you want to find out this MPT effect, right? So if you want to find out this number, so what you do is take the readings for which you have plus entries for that particular column. So plus, plus, plus for MPT, right? So you take those four numbers and you find the average. Then you take the other four numbers for which MPT is negative. So this value, this value, this value, and this value. Take the average of that and subtract the two averages that you have, right? The positive averages minus the negative averages, you will get a value of -1. So these are called the effects. Okay. So these can be very easily computed. In fact, software will do it. You don't have to do it by hand. So appropriate software will do it for you. There are many DOE softwares that are available, both free of cost as well as you can buy it for commercial kind of applications. So they will, once you give this basic data, in fact, it will also tell you what experimental design to do. If you give it the constraints and things like that, it will chart out the experimental design for you. It will select the run order based on randomization. And then once you enter the values of the experimental output measurements, it will form a table like this and it will calculate the effects for you. So what we get from here is the most dominant effect is this oven pressure, because in magnitude that's big. The second dominant effect is the material effect, because that is the next bigger number in magnitude. The third biggest effect is the interaction between materials and oven temperature, right? What is it called? Oxidation temperature. Sorry, T is oxidation temperature. So that has got an effect of -18. So it's got a negative effect, but that is a big effect. So there are these three big effects. The other effects are relatively small. So if I want to increase my shade measurements, right, I would try to increase the oven pressure. Can you see that? Because it's got a positive effect. So I'll try to increase the oven pressure. I can also increase this material, right? I will try to use material B if I want higher shade readings because that's got a positive effect on the shade. So those are my two big levers. And if M increases, right, what I'll do is I'll try to decrease the oven, the oxidation temperature. This is temperature, this is material, because M times T has got a negative effect. And increasing M, right, actually is good because of this positive effect of materials. So I'm going to increase M. So this is going to increase, but because this is a negative sign, I have to, and my interest is, let's say, in increasing the shade value. Therefore, what I'll do is I will try to reduce the oxidation temperature. So that together, all the three things that I do, increase oven pressure, increase material quality, and decrease oxidation temperature, will give me a higher shade reading. That is the intelligence I get about the system from the conducted experiments. Now, if I want to reduce, if we have to reduce the shade reading because a customer wants product with a shade reading of 150, what I'll do is I'll reduce the oven pressure because this effect is positive, right, of oven pressure. So if I decrease the oven pressure, it will decrease the shade value. I will also decrease this material from material B to material A. So material will go down, oven pressure also goes down. So how do I capitalize on this? Because material goes down and this is negative, what I'll do is I'll have to decrease this value. I'll have to decrease this value so that M times T will be positive because both are going in the negative direction. So this thing will be positive. Positive multiplied by minus 18 will contribute a negative value to the shade readings. So what we will see is the shade reading will go down. So decrease M, P, and T. When we wanted to, so if you want to do this effects calculation graphically, so this is what you do. Okay, so the material effect is going to be the mean of all readings with shown by this brown shaded ball minus the average value of all the experimental runs which are indicated by this red colored balls. All right, so that is what you see there. So in other words, we are taking the average of the experiments on the right face of the cube that corresponds to material being plus, and you're subtracting the average value of the experimental runs that are in the left face of the cube, which are runs made with material being at the low value, that means material A. So you're taking the average of these four readings and you're subtracting the average of the other four readings, right? You're doing this minus this. So the mean of these values minus the mean of these four values, so that you get a value of 22. So this is what you will see there. Okay, this is what you can see there. It's also indicated by this, right? So this right hand face is called plus face for materials, and the left face is called the minus face for material. What you are seeing there is nothing but what has been already described, and the difference will come out to be 22. You just do it by hand once to convince yourself that what I said is true, and that is exactly what you see here. So you can do it from a table or you can do it from a picture like this. Okay, typically when there is yet another way of coming to this value 22. So what we saw are two earlier methods, one from the table, and we also saw taking the average of the experiments on the right face of the cube minus the experiments on the left face of the cube, you get this 22. So those were two earlier ways in which we found out the effect, the material effect, to be 22. But there is also another way. For example, you take these experimental pairs, these two. The only difference between these two experiments is that in one case material A is used, and another case material B is used. The oven pressure and oxidation temperature are the same for these two experiments. And the difference between these two runs is 228 minus 189. All right, so we always do high minus low. So you get the difference to be 39. Between these two experiments, the only difference is the material A and B, nothing else. Oven pressure and oxidation temperature are the same. So if you take the difference between the high value for material and low value for the material, you get 259 minus 218, which is equal to 41. All right. Between these two experiments, the only difference is the material that's used. Otherwise, the other two factors are identical. Therefore, the difference is 195. This is 5. Okay. And for the last experiment, what you see is um, the difference between these two experiments is only the material being used. Oven pressure and oxidation temperature are at the same values. So if you do the high material minus the low material shade readings, you get a difference of 3. So if you take 39 plus 41 plus 5 plus 3 and you divide it by 4, you get 88 by 4, which is equal to 22. So that is the effect. Okay, so this is a third way in which you can compute the same value. And a fourth way will be we'll get an equivalent measure by doing regression. So all roads lead to Rome. Okay, so you can pick up your fancy method and then work with that. One interesting thing is this: the effect of material seems to be high in the lower face of the cube. You see numbers like 39 and 41, whereas in the top face of the cube, right, you get numbers like 5 and 3. Always when we use material B, you're always getting high values for shade, as these numbers like 39, 41, 3 and 5 show. All of them are positive, and we are doing B minus A, right? Material B is considered high, material A considered low. So we are doing that. In all cases, that turns out to be positive, which means material B typically gives higher shade value. All right. So our observation is that whenever we use material B as compared to material A, the effect is larger on the shade reading when we are in the bottom face of the cube as opposed to the top face of the cube. So the bottom face is low value for oxidation temperature, and the top face is high value for the oxidation temperature. That means the effect of material is high when the oxidation temperature is low as compared to when the oxidation temperature is high. So there is a significant material and temperature interaction. That is why this effect comes out to be dominant. Okay, that is one insight you can get from here. If you do the other kind of averaging or if you do things from the table, you don't get this insight. But in a diagrammatic form, and when you are analyzing your data like this, right, by taking these differences of pairs of experiments, and then you note the pattern, right? At the bottom face, the effect of material is larger than in the top face. So you understand that there is an interaction between material type and oxidation temperature. All right, and that comes out in this nice table that you see there. Okay, the effect materials times temperature is high. So that is what it is. And then if you look at the pressure effect, you compare the front face with the back face of the cube. The back face corresponds to pressure being high, and then the front face corresponds to pressure being low. And therefore, you take the average of these 4 measurements of shade, and then you take the average of these 4 measurements of shade, and then you do this difference, you're going to get the effect of pressure, which equals 36. All right, so that is also depicted graphically here with the back face indicated by plus for pressure and the front face depicted as minus for pressure. Okay, so you get the pressure effect to be 36, and that is exactly what we saw in this particular thing. The pressure effect is 36 when you do it from the table. And if you take paired-wise differences again, so the difference between this and this experiment, right, is only in the pressure. It is not in the other 2 variables, which are the oxidation temperature and the material. Material is A for both these experiments. Oxidation temperature is low for both these experiments. The only difference between these 2 experiments is the material, the oven pressure. So that difference comes out to be 29. These 2 experiments likewise are different in only the pressure being used, not in the other two factors. And the difference between shade readings is 259 minus 228, that is 31. And that is what you see here. Similarly, this is 41 and this is 43. Okay, so the point is, if you take 29 plus 31 plus 41 plus 43 and you divide by 4, because there are 4 such readings, you're going to get a value of 36. All right, and here there is not much difference, right? 29 and 31, of course, the top face again shows higher reading for differences in shade than the bottom face readings. Here it's 29 and 31, here it's 43 and 41. So there is quite a difference, but not as stark as what we saw with material effect. So it looks like there is a slight interaction between pressure and temperature as well, but it is not as much. So between pressure and temperature, yes, there is an effect, but then it is not as bad or as big. All right, so there is a certain effect. And you can do for the temperature likewise, and you can find that the temperature effect is negative of 5. If you do the same kind of ideas, whichever method you choose, either take the average of the top phase, which corresponds to high oxidation temperature, and the bottom phase, which corresponds to a low oxidation temperature. You take the averages and you subtract, you'll get a value of minus 5. Or you take the differences and between kind of paired experiments where only the oxidation temperature is different, you will get these numbers that are indicated within these rhombuses that you see there, or quadrilaterals that you see there. And if you take the average of those 4 numbers, you will get a value of minus 5. So that is the temperature effect that we also calculated from the table, right, using that idea. So all of these will give you the same answers. Okay, and if you want to do the material and pressure interaction effect, you have to kind of look at different combinations of experiments. So these experimental points show experimental runs where the material times pressure is positive. All right, the red lines filled circles show experiments where material times pressure is -1. So what you do is you take these 4 readings because they correspond to the plus, and that's what is shown in this figure also. These 4, right? So those are 4 readings where m times p is positive. So you take the average of those readings, and then what you do is you take the other 4 readings for which m times p is -1. So 1, 2, 3, and 4. These 4, right? 1, 2, 3, and 4. For this, m times p is negative, as also indicated in this particular diagram, using appropriate planes that they draw there. So you take those 4 measurements shown by red line filled circles, and then if you subtract the means of the first 4 with the next 4, in this case it turns out to be 0. So material times pressure interaction effect is 0, and that is what comes in this table as well. Okay, and so you can do the other interaction effects like that. So if you want materials times temperature interaction effect, so these are the 4 experiments where you see you have a positive value for m times p, right? So you connect these 4, right? So this is this plane, and then the other plane you will get by combining these 4 readings where m times t is -1. And then you do the averages and you subtract one average from the other, you will get the other interaction effect, which is equal to -18 in this case. So this is also shown here. A is material and C is temperature according to this representation, right? So basically, you will get the same readings as you got here, -18 for m times t. And if you do p times t likewise, what you will see is you have to take these 4. So these 4 are where p times t is +1, and these 4 are where p times t is -1. So if you take this plane and this plane, the average readings, and you subtract, you will get the p times t interaction effect. That is going to be +6 in this case. So that is what you would have got from the table as well. All right, +6 p times t. Okay, so there are many ways in which you can come up with these answers for the effects. And then when you do materials times pressure times temperature, the three-factor interaction effect. So these are experiments where m times p times t is positive. So these are like you know corners of a tetrahedron. Okay, and there are two tetrahedrons with four vertices each. So this, this, and this, right? This forms a tetrahedron. So that's the tetrahedron with a positive for MPT. M times P times T is positive, and there is the other tetrahedron where M times P times T is negative. So you take the average of the readings corresponding to the vertices of that tetrahedron, and then you would get the effect of MPT interaction. So that comes out to be -1 here. So whether it's from the tables or whether it is by a diagrammatic kind of an idea or any such idea, you should be able to compute the interaction effects and the main effects. Main effects means the effect of material, the effect of pressure, and the effect of temperature. Okay, you can also indicate the numbers you see there in the form of this dot diagram. So oven pressure has got a effect of 36, material has an effect of 22, materials times temperature has an effect of -18, so it's there. And then the other effects, right? P times T is 6. Something is like oxidation temperature has got -5. So I'm just taking numbers from this here, right? And I'm just plotting all that in a dot diagram like this. And as you can readily visualize, the big fellows are those that are away from the center and towards the extremes. So these three effects are the big effects, and you can put them to use in formulating a strategy. You typically go after the big fellows in these cases because that is where you will get the maximum return, because the sensitivities are big, 36, 22, -18. So the sensitivities are big. So you can affect a big change in the output by making a small change in the input. So this is like process gain, right, that we come across in a course like process dynamics and control. So if a process has high gain, a small change in the input will lead to a large change in the output. Okay, or if you want a certain change in the output, even by making a very small change in the input, you would be able to achieve that. So we are sometimes interested in sensitivities or gains being high. Sometimes we want the sensitivities to be low or the gains to be low. When we are talking about a disturbance, we want its sensitivity to be low because we do not want a small amount of disturbance causing a big change in the output. That is something we don't like. So again, like everything, process gain or process sensitivities or these effects can be double-edged swords, right? Sometimes they can help you, um, and sometimes they can work against you. Okay, so that is the idea. These numbers, the effects, what we call as effects, 36, 22, and -18, they are nothing but sensitivities or the process gains, and we can choose to manipulate them. You can also show it in the form of a diagram like this, right? So for material, you can show this, right? This kind of a diagram, so which says that it is going to be a positive effect, and the slope will be related to this value of 22, right? And then oven pressure will be related to, let's say, a value like 36, because that is the effect of oven pressure, right? So if you look at oven pressure in this particular representation, so it's all the same numbers, it's just represented differently. So this is a slope of 36, right, or equivalent to that slope of 36. So this slope is larger than this slope, indicating that this sensitivity of the shade reading to oven pressure is higher than the sensitivity of the shade reading to the material, right? And m times t, the effect is -18, right? So the slope is negative, and that would correspond to a value of -18. And the other effects, no, the zero effect for materials times pressure, and small positive effect for P times T, and -5 for oxidation temperature, I think, and -1 for MPT effect, right? So all of this can be shown diagrammatically like this. So people, when they look at it, they will understand which is a bigger effect, which is a positive effect, and things like that, right? So this is another way of representing the answers. Okay. So the conclusions for this would be that the idea will be to operate at high oxidation temperature, right? Why is that? Because it reduces the sensitivity of the process to material quality. So that is the most important thing here. In the bottom phase, right, the differences are rather high. If you look at this difference, it is high. If you look at this difference, it is high. If you look at this difference, it is high. If you look at this difference also, it is high. Whereas if you look at the top phase, right, this difference is very low. This difference is very low. All right. So the point is, if at all possible, operate at higher oxidation temperatures so that you can reduce the influence of material, right? Because material quality makes only 5 difference or 3 difference when the oxidation temperature is high. We already looked at this, right? So at high temperature, oven pressure should be set at a low level. So this would get shade reading of about 200. So basically, they are saying this, right? Something like this. This is a value close to 200. So the results are congruent with that, right? So use high temperature and use low pressure. So you will be at this point, which is going to give a value like 200. And you use material A or material B, it won't matter because this is 195 and this is 200. So the effect of material is not very big, right? So high oxidation temperature and low oven pressure. Material B or material A, both are likely to give a shade reading of close to 200, and you have to verify this by experimentation. So we can go to case study 2, where we are studying the effects of three factors, x1, x2, and x3 on the product yield. So x1 is temperature, and the actual readings are 120 degrees Celsius, which is coded as -1 low, and 140 degrees Celsius is the high value for allowed for x1, which is coded with a value of +1. Catalyst type, again, it is going to be type A or type B, so it's a discrete quantity. And the concentration of limiting reagent, low value is 0.25 molar and the high value is 0.5 molar. So you understand when we say 1, -1 and -1, we are talking about setting the temperature to 140 degrees Celsius. We are trying to say we will use catalyst type A, and then we will use a limiting reagent with concentration 0.5 molar. So using that combination of input factors, the yield is obtained as 17. That is what the experiment in the lab gives us. So it is 3 factors, and each of them is tested at 2 levels, no replicates, etc. So it's a standard 2 to the power of 3 design. So if you look at the way the numbers are written, it's written in a standard order: -1 + 1, -1 + 1, -1 + 1, -1 + 1, 2 minuses, followed by 2 plus 1s, 2 minus 1s followed by 2 plus 1s. The third column is 4 minuses followed by 4 pluses. So this is run in a standard order. It is indicated in a standard order, but it should be run. The experiment should be conducted in a randomized fashion. Okay, so but this is the data. After all that care has been taken, this is what we have got. So we can do a similar thing. I will leave you to verify these numbers because we have done this in great detail before, and this is the way this will look. All right, the diagrammatic representation using some software, that is how the 8 experiments can be represented as. All right, and basically whatever numbers are shown in brackets here like this, those represent the run order in which the experiments were conducted. Okay, so that is the, so whatever effects have been computed in this table representation, we can also show that in the form of the dot diagram, from which we can readily see, as we might be able to see from the table results also. In this diagrammatic representation, we can see that R, the reagent concentration, is a very important term because it has got a positive effect close to 16.25, right? That's what is seen here. And the second thing is between C and R, the catalyst type and reagent, right? The interaction between catalyst type and reagent concentration used, that contributes to a major effect, but the effect is negative. And then the temperature, right, T, has got a negative effect. That means if I increase the temperature, the yield is going to go down. That is what this negative effect says. The other effects are all very small. So the dominant effects are the reagent concentration effects, the two-factor interaction between the catalyst type and reagent concentration, and then the third largest impact is due to the temperature. So if you want to increase the yield, what you would do is you will increase the reagent concentration because it has got a positive effect. So I'll increase the reagent concentration. If I increase the reagent concentration, and because the interaction between C and R is negative, so what I'll try to do is I'll try to reduce the C. So that C times R will be negative, and that negative multiplies with this negative effect to give me a positive influence on yield. And I will also decrease the temperature because the effect of temperature is seen to be negative. If I decrease the temperature, the uh, yield will go up. So my conclusions will be increase reagent concentration, decrease temperature, and decrease the catalyst type. That means go for catalyst type A, right? Not catalyst type B. So that would be the conclusions of this particular study from just this kind of an analysis, right? So the point is a good organized experiment gives you the readings, and then you can quickly find out the effects using a graphical approach or a table-based approach, and you can visualize this in the form of a dot diagram. Or if you're numbers oriented, you can just look at this and say, well, this is the big effect, so I'm going to increase this because I want to increase the yield. And then this is the next big effect, but it's a negative effect which involves C and R. And since I'm increasing R and this effect is negative, I'm going to decrease C. And then this temperature has a negative effect, so I'm going to decrease T in order to increase the yield. So very quickly we can come to these conclusions, at least for this particular setup. Now, if you want to do it more formally, right, what you do is you model the data. So what I'm going to show you here is how you can use simple regression to achieve that. So here I have the big X matrix, a column of ones for the beta naught term, right? And then this is the beta 1 term for the effect of x1, beta 2 which is the effect of x2, beta 3 is the parameter that is associated with the effect x3, and the two-factor interaction between x1 and x2 is associated with the parameter beta 4. X1 x3 interaction effect is associated with parameter b5, x2 x3 interaction effect is associated with parameter b6, and the three-factor interaction between x1 x2 and x3 is associated with parameter b7. So you have parameters beta naught to beta 7, so you have a total of 8 parameters. So if you have 8 parameters, you have 8 experimental points, you can get a perfect fit of the data, and you can use the backslash operator. B is equal to x backslash y. What does y contain? Y contains the yield readings as column vectors. So that is y. X1, X2, X3 are all column vectors that contain temperature, catalyst type, and reactor concentration. So I'm not going into all of that. You know how to represent those experimental points as vectors, and then you can put together this matrix out of those basic vectors, and then you can do this backslash b is equal to x backslash y. Basically, it does x inverse y, right? It does the pseudo inverse and so on. So you get these coefficients. So this is our estimate of beta naught. This is our estimate of beta 1, etc., etc. All right, so this is our estimate of beta 7. So the equation right now is this. It's a perfect fit. Is it desirable? Probably not, right? Because our data is noisy, and I'm sure we have modeled the noise as well into this tightly fit equation. Because r squared is 1, that means sum of squared errors is equal to 0, right? Everything in the data y is captured in our model. That's why r squared is 1. We can't even compute r squared adjusted. All right, so this is the situation. It's a perfect fit because 8 points, experimental points, and 8 parameters, so there is no degrees of freedom left. So this is the thing, and so this is okay, right? For a start, you might just say this is a model, but then I was curious. I said, let me try this simpler model. Why I do that is I take these numbers, and if I look at the numbers, so this number is big, so I want a constant term in the model. This number is big, right? Though it's negative, it's big. So this is the x1 term, corresponds to the x1 term. This is small. This number is big. That corresponds to the x3 term. So x1 is good, x3 is good, the constant term is good. And then this interaction, which is x2 times x3 interaction is important because of this bigger value for this. So I am emboldened to keep the constant term. I'm emboldened to keep x1 x3 and x2 times x3 in my model. So I'm going for a reduced model of this type. And I do the regression again, including only the ones column so that I can estimate beta naught. I can estimate the coefficient of x1. I can estimate the coefficient of x3. I can estimate the coefficient of x2 times x3. So I do the similar stuff with a reduced number of terms in the model. So I get these to be the estimates of the parameters. I get the same values that I got here. The reason being, because this is a planned, well-designed experiment, your X transpose X matrix is called as diagonal. And because X transpose X is diagonal, X transpose X inverse is also diagonal matrix. So that is the nice thing when you do properly designed experiments like a factorial experiment. All right, these matrices have nice properties. And because this matrix is diagonal, sigma squared root of ci, right? So you remember this, which is the uncertainty term, etc. Those come out very cleanly because X transpose X inverse is diagonal. C matrix is also a diagonal matrix. So there is no covariance between the parameters, etc. That's why whether you do the estimates of this model or whether you do parameter estimates with this larger model of this type, the coefficients of those terms that we included remain the same. All right, so that is one side issue. So this is the current model right now that we have got from this regression. You can also use it using the stepwise tool. And what you will see here is r squared comes out to be 0.99, r squared adjusted comes out to be 0.98, pretty healthy numbers. Okay, pretty good numbers. And an estimate of sigma squared comes out to be, using the usual formulae that we learned earlier, the estimate of sigma squared comes out to be 2.63. And MSE is nothing but this sigma squared. So root mean squared error is going to be square root of 2.63, which is going to be 1.62. So that is the RMSE value. So the RMSE value is 1.62. The average value of y, if you take in this data set, the average value of y, let's say, is about, let's say 40. I'm not computing it, but I'm just saying it looks like it will be around 40. So 1.67, 1.62, which is RMSE divided by y bar, which is about 40, is about 3 or 4%, right? Something of that order, right? 1.62 by 40, which is y bar, my estimate of y bar, rough estimate. So that 1.62 by 40 is about, let's say, 3 or to 4%, let's say. That's a very small value. So this RMSE value is quite nice. That is also exemplified by this r squared and r squared adjusted value. In any case, if you look at these regression coefficients, what you see is if you kind of double 3.625, you will get minus 7.5. If you double this, you're going to get 16.25. If you double this, you're going to get, let's say, 14.75 negative. So please note the regression coefficients are half the value of the computed effects. So when you go to look at the effects, you get numbers like minus 14.75, plus 16.25, and minus 7.25. The regression coefficients happen to be, actually they are not happen to be, they are by certain for certain reasons, they are exactly half of the values of the effects that are computed. So the effects and the regression coefficients have this correspondence. That is why you don't have to do those effects calculation in the way that was introduced to you before. You can use it. You can use the regression framework, multiple linear regression framework, to come up with the most important variables, this, that, and etc. So all those things are very corresponding to each other, right? So they are quite related. So this is something that you might want to remember. Regression coefficients by design will be one half of the computed values of the effects. So regression framework is a very good integrated framework to analyze the effects of different factors, right? And as I told you before, we are doing sigma squared X transpose X inverse, right? I'm just showing that calculation for this particular example. This is, remember, this is the variance of beta. If you remember, this is the variance of beta. So what you see here is sigma squared is 1.63 squared, which is like 2.63, right? 1.62 squared is 2.63. and then this X transpose X inverse is a diagonal matrix. So sigma squared, a constant multiplied by a diagonal matrix, is a diagonal matrix. So this is the variation in beta naught term. This is the uncertainty associated, or the standard error associated with beta 1, beta 2, and beta 3 in the model, right? And the square root of that is the standard error actually, right? This is the square of the standard error. So the square root is going to be 0.57. So this can be used to compute the t values, etc. All right. So you get the t observed value to be these numbers. All right, and then if you look at the critical value, right, in this particular case with 4 degrees of freedom, because you have 8 data points, you have 4 parameters, so the degrees of freedom are 4, and therefore what you do is you look at the critical value, you get 2.78. All these numbers are bigger than 2.78 in magnitude, which means these are statistically different from 0. That means all the 4 estimated parameters are statistically different. They are not like 0. So the model is okay. And therefore, as we said earlier, high reagent concentration, catalyst type will be low, and you also want to operate at low temperature, right? So that is what we concluded here. High reagent, low catalyst value, and low temperature. The same conclusions as before, because we are working with the same kind of numbers, etc. So you can also do this, right, more formally. Here I've glossed over the calculation of the t values, etc., to test for parameter significance and all that, simply because we have this wonderful tool called Stepwise. So basically what you do is you have a bunch of comment lines in your M file, and then you write your x1 value, x2 value, and x3 value, because please note the use of this apostrophe here, which says that it is going to be column vectors. So I replace write x1 as a row vector and put an apostrophe at the end, which means it will become a column vector. So these are the yield values y, and this is the big X matrix, right? And as you know, in stepwise, we don't have to accommodate for the constant term, because the stepwise tool will automatically involve the constant term as intercept. Okay, so I formed the big X matrix, including the 3 linear effects, the 3 two-factor interaction effects, and 1 3-factor interaction effect, and I just do x stepwise x comma y, and I'll get this GUI, and then it says move node terms. All right, so it just says let's just do this. So what I'm trying to do here is I went and chose everything. So I'm now trying backward stepwise regression. The forward stepwise regression, when I started, it basically says move node terms. So I am adopting a backward stepwise regression where I include all the terms in the model, and then I'm going to eliminate the terms that are deemed unnecessary. So at this stage it says move x2 out. So I move x2 out and I follow a sequence of recommendations that this tool provides me. And finally I come and stop here, right? So here what it shows is the r squared is 0.99 and the r squared adjusted is 0.98. The p-value for the f-test is this value, which is smaller than 0.05. So I say the model is adequate. So the intercept is 38.125. That's the constant term in the model. And the model includes 3 other terms. It includes the reagent effect. It includes the temperature effect. The reagent effect is positive. The temperature effect is negative. And then the interaction, right, between reagent concentration and catalyst type, which is a negative effect. So that is also included here in the model. So we get the model as we had before, 38.125 minus 3.625 times x1 plus 8.125 times x3 minus 7.375 times x2 times x3, which is nothing but x6, the 6th term in my big X matrix. All right. The t values are all indicated here, and corresponding p values are shown here. So for all the terms that are included in the model, the p values are smaller than 0.05, which means the effect is significant. That means those parameters are statistically significant, and graphically also you can see that 95% confidence intervals for those parameters do not cut that value 0, right? This dotted line, it doesn't cut. The whiskers are well to the left or to the right of this 0 value, right? For the terms that are not included, you can see the 95% confidence intervals, they cut the zero value. So that is why these are insignificant terms in the model. So at this stage, um, this is what we say. We can export the output at this particular stage to the workspace, etc. So we have already seen it, right? So these are the beta values, the point estimates, the lower confidence interval and upper confidence interval for this parameter. For this parameter, the lower confidence interval and the upper confidence interval, 95% confidence interval. And for this parameter, the lower confidence interval and the upper confidence interval, right? And all that is shown there, R squared adjusted, RMSE, everything that we had calculated in another way earlier. So all of these numbers are correct, right? So we have the same model which we obtained earlier. So then what we can do is we can use that model for optimization purposes, right? That would be the goal of making a model, right? We would like to find out the conditions x1, x2, and x3 that optimizes the value of yield, that increases the value of yield, or that maximizes the value of yield. So we can do the optimization with Excel solver, or we can do the optimization with a tool like MATLAB. Okay, so here I've demonstrated that with Excel solver, and you can do the same thing with MATLAB. So in this particular case, right, x1 and x3 are continuous variables. All right. So I'm going to allow, when I optimize, I'm happy to allow a 25% deviation from the experimental limits. That means I'm allowing 25% extrapolation because they are continuous variables. All right. Therefore, I will set the low value for x1 to be minus 1.25 and the high value for x1 to be plus 1.25. The experimental values were between minus 1 and plus 1. So in order to increase the yield, I'm just going to allow for a 25% extrapolation on both the positive and negative sides for both x1 and x3. So the lower bound for x1 for optimization will be 1.25 and the upper bound for x1 will be plus 1.25. Same for x3 as well. Now x2 is a discrete variable and it can only be type A catalyst or type B catalyst. So it has to be either minus 1 or it has to be plus 1. Okay, so what I'm also doing is I'm going to scale x2 and announce it as binary, so 0 or 1. So what I'm doing is I'm introducing a new scaled variable called x2s, which is going to be x2 plus 1 divided by 2. So when x2 is minus 1, that means catalyst type A. When x2 is minus 1, it will be minus 1 plus 1 divided by 2, which is going to be 0. So when x2 is equal to minus 1, x2s will be 0. And when x2 is plus 1, which means it is catalyst type B, x2s will be equal to 1. Okay, so I'm just going to do that to make x2 appear like binary. Okay, 0 or 1. So when x2s turns out to be 0, it means x2 actual is minus 1, which means catalyst type A. And when x2s turns out to be 1, then it means x2 is actually plus 1, which means it is going to be catalyst type B. Okay, so we are going to set up our optimization problem using x1, x2s, and x3. x1 and x3 will be continuous variables, and x2s will be binary. x2s can only take values either 0 or 1. x1 and x3 are allowed to go anywhere between minus 1.25 and plus 1.25. So this is our model that we got from stepwise regression. So what we are doing is we are converting this x2 using this transformation, right? So we said x2s is nothing but x2 plus 1 divided by 2. Therefore, x2 is going to be equal to 2 times x2s minus 1, right? So wherever you see x2 in the original model, we replace that x2 with 2 x2s minus 1. So that is why you see that here, right? Instead of x2, I have 2 times x2s minus 1 in MATLAB language. So that is what it is. So this is our Excel spreadsheet. So I go to an Excel sheet and then I just say decision variables. This is something that I type. So I type x1, x2, x3 to just indicate to us what different numbers are. These are the three numbers. These are the handles, right? These are the decision variables that can change. X1 can go between minus 1.25 to plus 1.25. X3 can go from minus 1.25 plus 1.2 plus 1.25, and X2s can either be 0 or 1. Okay, that I'll set it up later, but right now I'm just giving the value 0, 0, 0 for that. And then I'm also creating labels, right? Just text to just indicate that the objective is going to be entered here, and the objective is to be maximized, right? That's our goal. And the physical, I also have a provision where I kind of calculate the value of the physical value of x2, right? So that is something I ask Excel to show here. So basically, we know that x2 times x2s minus 1 is nothing but our x2, right? This is what we know. And therefore, if x2s is 0, 2 times 0 minus 1 is going to be minus 1. So when x2s is 0, here it will show us minus 1. And when x2s turns out to be plus 1, if it turns out to be plus 1, then x2 will show to be plus 1 here. So this and this are connected. And this value, right, the y value is connected with all the three values of x1, x3, and x2s. So this is where I enter the formula that is shown here, right? So I have to enter this formula in that particular cell. Okay, so basically the three decision variables, this is the model equation in terms of x1, x2, s, and x3. And this is the relationship between the actual value, the physical value of x2 and the value of x2s. All right. So then what I do is, so if you go here, right, on this cell, I have to type out this formula. So I'll have to say y, or this space, right? I go here and say equals 38.125, then minus, what is the formula? 3.625 times this value, this cell, right? Which is, let's say, D5. So do that appropriately, right? D5. Then the next term is plus 8.125 x3. So plus 8.125 x3 is nothing but D7, right? Please follow the proper Excel commands for this. If you're doing it in Excel, if you're doing it in MATLAB, you can use something like fminCon for that, right? And then you have minus 7.375 minus 7.375 times 2 times x2s. So x2s is d6, 2 times d6, then minus 1 times you have x3, I suppose, right? x3. So x3 is nothing but d7. So this is the formula that has to be entered in this cell, right? So that is, I'm sure you are aware of that. And then what you do is you invoke the solver in Excel, and then out comes the solver, and you can set, as we have seen earlier, you can set the objective. It's going to be in cell D10 because D10 contains the value of the formula for y, and you're trying to maximize it. Therefore, you click on this max button there, and then the decision variables are in D5 to D7, so you indicate that here, right? So the cells D5 to D7 are to be changed in order to maximize D10. All right. And then you give these constraints using this add feature. You add constraints on x1, the upper bound, the lower bound for x1, the upper bound and lower bound for x3, the fact that d6, which contains x2s, you say it's binary. So there are these options that are available. When you add constraints, you can do that. And then you can just use the solve button, right? When you do that, you get these to be the solutions, right? And what the model says, and based on the extrapolation that you allow it to do, it says, well, use catalyst type -1. That means x2s turned out to be 0, which means it says use catalyst type low, and use as low value for x1 that you would allow, as low value for t, and as high value as you might allow for reagent concentration R. And this is exactly what qualitatively we said, right? Increase R, decrease T, and use the catalyst type A. That is what we said. And optimizer also tells us that And then the optimizer says if you use x1 is equal to minus 1.25 encoded units, x3 is equal to plus 1.25 encoded units, and if you use catalyst type A, the low type catalyst, your yield will be as high as 62.03%. Okay, so this is how you do experimental design. You come up with the models using a tool like Stepwise, and you put that model into a MATLAB FMinCon kind of a solver, or using Excel solver to find out the best values for the three factors here. So basically these are the conclusions, and in terms of numbers, x1 is equal to minus 1.25 means use 117.5 degrees Celsius. All right, and catalyst type A, and then X3 is plus 1.25, it means concentration of 0.531 molar, because minus 1 in coded units for X3 corresponds to 0.25 molar, plus 1 corresponds to 0.5 molar. Okay, so the question is, what does plus 1.25 mean, right? So you can compute that to be 0.531 and uh, confirm if my calculation is all right. And what you will do in the lab actually is you will set this, so you'll get permissions, safety permissions, etc., and then you will try this experiment with 117.5 Celsius, reagent concentration of 0.531, and using catalyst A, you will do an experiment. And if it gives a value like, let's say, close to 62, it may not be exactly 62 because our models could be slightly incorrect. Let's say even if you get a value like 55, let us see whether it's got any benefit. So we have gotten 55 before, 56 before, but the model tells you can go up till 62. So even if you get a value like 59, using those settings for x1, x2, x3 that the optimizer told us, we would be much better off. A 3% yield can mean several hundreds of thousands of dollars annual savings, right? Depending on the material that is being produced. All right, so this is a case study that you can take, a full case study involving design of experiments, modeling and optimization, and back to experimentation and verification. Okay, so that is the, please try to implement the same optimization in MATLAB as well. That will be useful. And finally, case study 3 is an interesting one. So it's a 2 to the power of 3 design in a semiconductor process, etching process, right? So you have gap, gas flow rate, and power to be the three input factors, and etch rate is going to be the output value of interest. So what you do is you do duplicate experiments for each setting. So you have 8 settings, but you do total of 16 experiments. So at low for gap, gas flow rate, and pressure and power, one time you get a value of 247. Another time when you do it as a another run later in a random order, you get a value of 400. So there are two readings. What you do is you take the averages, right? So run 1 and run 2, you can take the average and you can use that as the average reading. And the rest is actually exactly like what we did before. Once you have the average value of these two runs, then you can compute the effects here, and then you see some really big effects here, right? And here. So always, right, these are practical problems. These are taken from real world situations. You always see the interaction effect. Some interaction effect is always dominating, right? For example, the gas flow direct effect is very small here. This is quite small compared to, let's say, this two-factor interaction, which is the most dominant after power. So the two-factor interaction terms are dominant. Sometimes they are bigger than even a main effect. So do not underestimate the power of interactions, right? And with that, we complete our discussion of factorial experiments. We will catch up in a different video. Thank you.